Okay, so in this redox titration, it's known as the iodine thiosulfate titration, and in the burette you have thiosulfate. During the titration, that will be oxidized. You can see it's losing electrons. And in the conical flask, you have the iodine, which is being reduced. It's gaining electrons. So this will always be the case. Thiosulfate will always be oxidized. The iodine will always be reduced. Combine these two half equations, you get this overall equation here. And you can see that there's a 2-to-1 ratio between the thiosulfate and the iodine. So this is very specific. I think, oh, how often do we really need to know the concentration of iodine? But we can get the iodine from secondary reactions. We do another reaction first and then do the titration. So the first reaction we do will release or liberate the iodine. So a common one you'll see, it will be generally different oxidizing agents. And here's one where it's reacting with copper 2+. So there's quite a well-known chemistry A-level experiment where you work out the amount of copper in a brass screw, and you dissolve up the copper in acid to release copper 2+ ions, but the copper 2+ ions aren't going to react with the thiosulfate. So what you do is you add potassium iodide, because you want those iodide ions. The iodide ions here, you can see, have reacted with copper 2+. It's made copper 1 iodide, CuI, copper 1 iodide. So it's still an ion, but it's Cu+, not Cu2+. And importantly, it's liberated, released the iodine. The iodine's a brown solution, and this whole solution, together with the precipitate, because it'd probably be too much effort to separate it, will be titrated to work out the amount of iodine you have. From the titration, you'll know how much iodine you have. If you know how much iodine you have, you can work back to work out how much copper you started off with. But you can see that the ratio of iodine to copper is 1:2. The iodine to thiosulfate is 1:2. So basically, when you work out how much thiosulfate come out of the burette, you'd halve it to get the iodine, and then once you know the iodine, you double it again to get back to the copper. So you'll be on the same number in the end. Another example, you could do the chlorate time. You'd add potassium iodide, again in acid conditions this time. So this could be from bleach, and again it liberates iodine, and that could be titrated. And you can work out, if you know how much iodine there is, you can work backwards to work out how much chlorate ions there are. One thing about the iodine thiosulfate is it's got a bit of a tricky endpoint. Iodine, which will be in the conical flask, is a brown solution. As you're titrating it with thiosulfate, it will gradually get lighter and lighter. But this wouldn't be a very good endpoint because it's not a sudden change. It's a very slow, gradual change. So once it's gone from brown to what's also called a straw yellow, we add starch, and that turns the whole solution a very strong blue-black. Now this is quite strange. You don't add starch straight away. And the reason for that is when you have a huge excess of iodine, starch and iodine form a complex which stays blue-black, irreversible, and that won't work. We need it to change colour. So you have to remove quite a lot of the iodine first, but still have some present because it's still yellow, and the starch goes blue-black, and then you carry on adding thiosulfate from the burette, the same batch of thiosulfate, keep adding it from the burette, so you're adding on to your titra that's still increasing. Keep adding on thiosulfate, and eventually the blue-black colour goes colourless or is decolorized. Now sometimes that's hard to see as well, because if you think back to this bit here, it'll go colourless, but then you have a white precipitate still. That white precipitate, although it doesn't take part in the titration, will still be there, and so you don't necessarily see a colour solution. You might see a colour solution with a white precipitate floating about in it, depending if this happened or not. I mean, if it was this one, then you wouldn't have that problem because the chloride, iron, water obviously have no colour.